Hello, 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 everybody. Welcome. And before we start, I would like to thank you all for joining us today at reInvent on this crazy week-long adventure. Thank you for coming here in person after a couple of tumultuous years we had. It's nice to see your faces, even though some of us will still need to wear masks. My name is Oleg. I am one of the many engineers who work on Amazon S3. And today I'd like to talk to you about building data lakes on Amazon S3. We'll walk you through several aspects of this process, and we hope that the lessons we will share will apply whether you're just considering building a data lake on Amazon S3 or have one in operation. We'll chat about what data lakes are. Do you even need one? Is it just all a marketing ploy? Challenges we may encounter in operating them. And most importantly, at the end, how Amazon S3 can help you. The subject matter is enormous, and if I was trying to go deep on every one of them, it would be like boiling the ocean. So we designed this presentation as a jumping off points. Other sessions at reInvent, as well as a very wide AWS documentation, can help you jump off into dive deeper into more specific subjects. So what is a data lake? Chances are you have seen headlines like this. Businesses always rely on data to make important decisions, to delight their customers, to improve financial efficiency. Some of the questions your executives may be asking: who are my customers? What signals are they sending me explicitly or implicitly? And sometimes the implicit signals, such as how my product is being used, what is the utilization rate, how my customers practice it, actually much stronger signal than what customers tell you directly. Which features should I launch or phase out? Which makes the most attractive, which area is the most attractive for expansion? Which markets should I enter? And the questions are endless. What do those questions have in common? They're all about big picture. And they all need data, but any kind of data? Businesses collect a lot of data, but what is enough? What is right data to answer this question? Definition of data from Wikipedia is raw individual facts and statistics independently collected from multiple sources. By the very definition, it is granular, and you may not be able to see forest for the trees. What we really need is something like this. We call it information: processed, organized, and structured data, which provides context. Data becomes information when it enables decision-making. So for that, we typically need to cleanse, join, aggregate, present it in a digestible form, because humans love graphs and charts. And based on that, you can get to insight. And again, from Wikipedia, understanding the cause and effect, enabling decision-making. So data has to travel to become helpful. Data needs to travel to enable decisions. And where do we put all of this? What do we need? Something like this. In this quote, centralized repository that allows you to store all structured and unstructured data in any scale, it seems reasonable, but pretty self-evident, and maybe even too self-evident, and maybe overly verbose. How did it come about? And more importantly, how do we build one of those? And what do we need to think about with building them? And what are the challenges? And is it just very simple? To answer all this question, we're going to attempt to take a very brief trip down the memory lane. And to make the journey a little bit more interesting, we're going to continue using water-related metaphors throughout, which brings us to data puddle. A long, long time ago, in a universe far, far away, also known as the 90s, you might have had an architecture that looks something like this. You may have a relational database, file server. You may have a bunch of services running there, typically not that many, writing logs. You may have email management system, and so on. So we have all of this. Can we just use this directly? Yes, we can. Can we just query it? And this works very well. And it was the first step of giving businesses what they need. How far is it taking us? Let's look at impromptu scorecard. The quality, good. Relational databases are really good at aggregating data and cleansing it. There may be some disjointedness in your data sets, but ultimately you don't have a whole lot of databases at this point, so that works well. Complexity, very low. It's basically point and click. Performance, also pretty good, because making aggregations and creating reports is what relational databases are fantastic at. In cost, well, maybe you need to upscale your relational databases a little bit, but other than that, things are looking pretty good. So how far is it taking us? Humans in general love things that work. And if you give humans or businesses something that they can use and find productive, they're going to want to use more and more and more of this. And we observe that as far as businesses and data, something like this tends to happen. First of all, you have the explosion of volumes of data. If you have this reporting system, it has become successful, then more data is going to get placed into it. In addition, if it becomes successful, more data sources will be utilized. And finally, more people are going to want to look into it. So initially, it might have been only C-level executives looking in your data, but now you have marketing and operations and any number of departments. So where is this taking us? Well, we started simple, and it may look something like this, but over time, it becomes this. You have more systems, and as you can see, some of them are becoming disjointed. You have more users interacting with all of the systems, and the complexity of the architecture is slowly increasing. And so you may end up with something that's looking like this. So what does it all mean? What are these little fires everywhere? Well, more use cases requires more systems. More queries requires more resources. And while relational databases are fantastic at executing reports, when you apply mixed and hybrid workloads, such as transactional workload, when orders are getting created and shipments getting tracked, and analytics at the same time, you experience log contention, normalization may get in the way, and secondary indexes may explode. Generally speaking, your database is not going to be in a happy place. And as a result of which, things get slow. And another thing is happening here. You can see that data sets are getting disjointed. So how's a scorecard looking? It's not as good. Scale, or practical limit of this kind of system is probably tens to hundreds megabytes. And it relies entirely on vertical scaling. Quality, well, you start having disjointed data sets now. Complexity of your system is increasing. Performance may start tanking as your databases get under higher load. And cost is increasing because not only are you having to invest in more servers, you also have your DB admins working on them 24/7 to keep them up. And there is something else happening, more insidious, durability. The first axiom of any database system, thou shalt not lose data. And databases under load do tend to do just that. So as an outcome, your customers become impacted. And in this particular case, we're talking about two classes of customers. You have the external customers that may be using your system directly, and all of this analytics queries running all over it may slow them down, and that is a huge problem. But you also have internal customers that get affected because all of these reports become very slow. So obviously, we cannot continue like this. So what happens then? We need to rethink something. What might it look like? Well, we made an observation that in order to get to insights, we need to do something with the raw data. And so our approach was to start querying it. And that was meaningful, and it got us far. But can we do something better? Well, what if we did something like this? What if instead of doing this on the fly, we tried to transform the data and extract aggregates and important information in advance, as opposed to directly querying your raw data? And so you can start by extracting the data from multiple data sources. You can transform them and cleanse it. But more importantly, you can now join them, which means having multiple systems no longer gets in your way. And then you can load it into a single store. And that solves disjointedness, improves performance, improves data quality. And this is when the very familiar term ETL now appears, which stands for extract, transform, and load. So what would the architecture look like? Let's consider what we call a data pool. Actually, they were called data marts. They were very common in late 90s and early 2000s. And typical architecture may look something like this. You have a wide range of data sources. You have ETL pulling raw data out of data sources and putting it into a specialized store. In fact, this was the period when specialized analytics stores appeared. And this is where things get very exciting. The store can be made super special now, specifically designed for analytics. Concept of OLAP, online analytics processing, appears, multidimensional models, analytics queries, and real-time pivot tables. At this point, your business analysts are delighted because you can slice and dice your data, aggregate it on demand, and everything works beautifully. So how are we doing overall? Things are improving across the board. Scale, we can maintain hundreds of megabytes to tens of gigabytes now. That's much better. Data science are joint again because you have this big, giant, beefy analytics store. Complexity is very manageable because you have this very nice pipelining architecture. Your performance is also improved because your data sources and your analytics data are completely separate now. And cost generally is improved because you can scale these things independently and there is no crossfade effect. And durability is also improved because, again, your original data is not affected. So we have gone through something very interesting. We have re-examined the specific characteristics of the system and then transformed an architecture. And it allowed us to scale up quite dramatically. So are we done? You will probably get used to this slide over the course of this presentation. This keeps happening. For all of the reasons we have discussed, everything is growing again. There is more data, there is more use cases, there is more people. And as a result, you're probably guessing what you're going to see. You started here, and then you might end somewhere looking like this. And here you see the multiple databases start appearing again. ETLs are becoming complicated. And as the time goes by, something like this might start happening. But what is going on? Well, first of all, it's cardinality explosion. Analytics data is incredibly useful, but it tends to get huge because it grows exponentially. Analytics databases also get on a high load and now requires splitting. Disjointedness appears. ETLs get substantially more complicated, and in fact, they may start affecting your data sources at this point. So this is not looking too promising. How are we doing overall? Well, not as great as we were hoping. Practical scaling limit of this is probably close to 1 terabyte, and it still very much relies on vertical scaling. Quality, datasets are disjointed again, and performance start affecting them. Complexity has grown. Performance is suffering because of the overload of the system. And cost. Cost is a particularly insidious aspect here because this specialized databases typically require explicit vendor buy-in. You may be paying a lot of license fees, and at the same time, there is maybe 7 people in the world who know how to operate them. And so the cost across the board becomes complicated. And as you scale them up, you rely on more and more cutting-edge hardware, and that is expensive. And durability across the board starts suffering because ETL may affect your data sources. And in addition, how do you back up? And again, this is early 2000s, 1 terabyte of data. There is just not a way. And so familiar things happen. Your customers are impacted. So what can we do? Also, something needs to happen. We need to rethink something. Now, if you remember, the first time we observed that insights and raw data can be separated and we don't need to look at them at the same time. Is there any transformative observation we can make now? Well, one thing that keeps coming up over and over again is this, vertical scaling. What it ultimately comes down to is a single thing cannot grow indefinitely. And that thing may be hardware, software, or a system. Why? Well, cost. Because the bigger a thing gets, the more specialized it typically gets, and the more expensive it becomes to operate. Interestingly enough, laws of physics get in the way because your hard drives can get only that big. And at that point, Moore's law starts breaking down again because you no longer have your CPUs doubling frequencies every year. And also reliability. The blast radius of a failure of a single thing should not be catastrophic, and that's exactly where we're at this point. And the larger a thing gets, the more fragile it becomes. And so a shift in paradigm is needed. And so distributed systems appeared in the early 2000s and really exploded in the mid-2000s because this kind of thing was happening to everybody, and the industry started very heavily investing in this particular area. This in itself is, of course, a huge subject, but fundamentally there are 3 assumptions underneath distributed system. First of all, instead of scaling up, we're scaling out. We don't make a thing bigger, we just rely on more things. Second of all, we start relying on commodity hardware. We no longer try to build super specialized and very expensive things, primarily because of cost and also because of operations. And finally, and this was revolutionary, built-in fault tolerance. We expect things to fail. We design for things to fail. So this all sounds fantastic. What does it look like when it comes to what we now call data reservoirs? So you probably all remember the elephant. And this is where the concept of a big data appeared. Hadoop revolutionized this space. It also did a lot of other interesting things. One wonderful aspect, it was the first attempt to separate compute from storage. HDFS was used for storage, MapReduce for compute. And in addition to that, HDFS was a scalable, elastic, and a singular thing. Because as you recall, we keep on going through building a system, building more instances of the system, disjointedness appears, and we have to come back again. Here we came back again at a much, much higher scale. And more importantly, Hadoop has created a vibrant ecosystem. So it started with just relatively basic MapReduce, and then consensus, scheduling, SQL-type querying, ML appeared all on top of it. And this might sound like an obvious observation, but here's what it did to your data. Just because your data was in HDFS, you can now do new things to it because of all of these new products that allow you to do this. So back to reservoirs. Let's call this a data pond. So the architecture may look something like this. The raw data gets exported from data source and placed into HDFS. And ETL then runs on top of it. So now you have both aggregates and raw data inside HDFS, which means your data sources are no longer used for any analytics needs. And you may also want to load some of the aggregates into reporting databases and use familiar reporting software. So how far does it take us? Well, improvement across the board. This kind of scale can actually go up to petabytes of data, which is wonderful. And that's probably as much as we're ever going to need, right? The quality, all data is put together, and that includes raw data, aggregates, anything in between, so you can query it all at the same time. Complexity is interesting here, because it is not that it's low complexity, it's low complexity to the user. Hadoop handled a lot of very, very complicated things, including consensus, data repair, and various other aspects of it. And that was very revolutionary for its own time. Cost is actually quite manageable because we're relying entirely on commodity hardware. And durability is particularly interesting because it was specifically designed for failure. In practical terms, it actually, in default configuration, you needed to lose 3 data nodes at the same time to just lose several megabytes of data. But in addition to it, ecosystem was something that was very important. And as the time went by, you can do more and more things with your data. That is very exciting. So that has got to be enough. We have petabytes of data. We can do whatever we want with it. Everybody can put data into it. But then this, of course, is still the case. HDFS is super elastic, and so now you have new type of data in it. You have you load your device data. You maybe start loading media. Another thing that's happening at the same time, and what distributed system enabled, is social media. And social media produces basically fire hose of really, really substantial volume. And you want all of this to make decisions. And more people want to access this data. And so I bet you know how it's going to look like. You end up somewhere like this. And if you're not careful, you may end up somewhere like this. Because another thing about Hadoop is that just because you can put as much data into HDFS as you want, you sometimes don't even know where things are anymore because it is a file system. It doesn't come with any sort of a metadata catalog. Products appeared later on to compensate for it, but it certainly wasn't an upfront decision. And so our scorecard is looking sad again, unfortunately. Turns out HDFS does have a scaling limit, around 6,000 to 7,000 nodes and maybe 20 plus petabytes of data. If anybody has ever run an HDFS cluster this size, you know what starts happening. Your data nodes start flapping. Hadoop spent a lot of time repairing them. Maybe your name node starts falling down. Things get complicated. In terms of, and that affects quality of data, again, because now you're forced to build multiple Hadoop build-outs. Performance get affected, of course, and cost, because clusters get huge, and so do ops. And so in addition to it, if you try to do it yourself, because you have to physically house all of these servers, you need to build out data centers now, which means real estate, power, cooling, security, physical security. Durability, HDFS at a high scale can absolutely lose data. Performance, I briefly touched on, but it's really interesting. It decreases with scale, but different problems start emerging. Because if your fleet is not entirely 100% homogeneous, which is really difficult to achieve, resource skews may appear. Some may have high CPU, some may have high I/O, some network limits may get saturated, disk may get full. In the end, it becomes very, very hard. And in addition, this. Discoverability, as we discussed, we have a data set this huge, it's very difficult to understand where things are. And in addition, this is the time when the governments of the world start legislating how you should handle your data to protect consumers and citizens. And implementing all of this solution, enterprise-level compliance and security regulations, meeting them is actually very hard. And it's also not at the core of your business. And so, familiar slide. So let's go back. What do we actually need? What are we trying to build all of this time? We've seen the sentence before, but now let's go over it. A centralized repository. Centralized means singular. Repository is different from a file system. It means it's something that can be discovered. It's something that can be reasoned about. That allows you to store all of your data. And the key word here is actually store, because it means not lose, and this is where durability comes in. Your structured and unstructured data, and that includes things like media and social media data and aggregations and raw data and device data and any number of things at any scale. If you remember, it's at any scale that kept us pushing into the red category. So why is this so hard? Why do we keep going through the same cycle, and why is it becoming so difficult? Well, there's two vectors in play here. One of them is business needs. So we started with a relatively small set of requirements, and then they continue expanding. At the same time, our scale keeps growing as well. And as a result, we end up with something like this. We seem to be going through the same unfortunate cycle. And if we look deeper at the cycle, this is what it looks like. You start with innovation. You realize you have a problem, you design a new data store, and it's by far the hardest part. You have to challenge existing assumptions, design your architecture, and get it right, which is very hard and very complex. Now, we're all engineers, we're all capable of doing this work, but the thing is, while we're doing this work, we are not really focusing on the actual needs of our business. Not only that, but say you have designed this beautiful thing. Now you have to rebuild everything. You have to move your data to it. You need to make sure it's secure again. You need to shift all of your systems. And that is money, and that is time, and that is you again not focusing on your business. Then you're in the happy phase. Your data sets are growing. Everybody's happy. But then as the scale gets up, sometimes things start breaking down again. And we need to repeat it over and over and over again. So it seems like there is a need for something that can keep up with the ever-changing requirements at scale at the same time, something ideally out of the box. And as you can imagine, being where we are, I would like to mention Amazon S3. You probably guessed it. As Amazon S3 will continuously innovate on your behalf, so you don't have to. So now you can focus on your business. Now, I've mentioned all of these hard things that were coming up as we were building our own data store. So why does Amazon S3 help? You shouldn't just take my word for it. You have seen this diagram many, many times over the years, and I'm sure during this conference as well. I'm not going to get very deep on every single subject, but I want to cover the points that we discussed as very difficult and very hard to get right. One of them is scale. This is what really was getting us before. Amazon S3 doesn't require explicit scaling. It basically just works. We're going to talk about best practices to make it work better and to make it work more productively, but basically it just works. Durability, 11 nines of durability. You have heard this number many times, I'm sure. What does it mean? Well, one of the ways of thinking about it is that if you store 100 million of objects in Amazon S3, you can expect at max to lose a single object once every 10,000 years. That's pretty impressive. Cost is basically pay-per-play. It's competitively low, and there is a huge range of options, which we're going to look into in a little bit. You pay only for what you use. And as far as security, compliance, and audit, we have a group of specialists that continuously working on it, continuously following all of the regulations. And finally, ecosystem. AWS itself provides a huge of services, but also a huge group of partners provides a group of services that help you build your data lake. So how do you actually build one, and how do you go from here? Maybe you have some data in Amazon S3. Maybe all of your data is Amazon S3. We're very happy to hear about that. Or maybe you're just thinking about setting it up. we're going to go through some recommendations to help you get it further and get it right. So if you remember a single slide from this presentation, I would like for it to be this one. The first very important point is a data lake requires a design. Some decisions need to be made up front and they need to be explicit. Lift and shift is possible. Yes, of course, you can just copy your data from HDFS or wherever it was to Amazon S3 and maybe run your workloads on EC2 instances, and that will work. But it's possible, but sometimes it's not the most optimal for a variety of reasons, which we get into. Without architectural changes, some old pains may manifest again, and we will talk through this. It is also an opportunity to consider your current and future business needs, and this is where the ecosystem comes into play. So a lot of decisions that you make up front really matter, and you need to think about the data structure, where it's coming from, at what cadence, who and how is going to be using it, what is the access model, the format, the placement. And all of this decision impact how your data fits into the ecosystem. They also impact how you implement your security and compliance, because the shape of things defines what kind of mechanism you can define on top of it. Now let's get a little bit deeper into this. These were the 4 major factors that we had to struggle with when we're trying to build data reservoirs on our own: scale, cost, ecosystem, and security. When I mean security, compliance, audit, combination of those. So let's start with scale. So let's revisit basics. I'm sure everybody in this room probably knows this. The basic structural unit in Amazon S3 is a bucket. It's an S3 resource, and you can think about it as a mount point for your S3 data. Within bucket, live prefixes. Now, one thing I would like to point out is that Amazon S3 is an object store. It's not a file system. And so the distinction is that it has a flat namespace. There is no explicit hierarchy. But there is a concept of prefix, which you can think about as a grouping factor, basically a logical directory, if not a physical one. So this is the next layer of data organization. And this is actually important because you can use prefixes in your security policies, in your access policies, in your lifecycle transitions, and so on. And in addition, object tags can be used to mark objects in Amazon S3. In tags, it's really just a combination of key-value pairs. You can have up to 10 on them, and there are some examples here. And again, this is a powerful mechanisms by which you can further utilize for a variety of processes going forward. So for the most part, before I start talking about this particular slide, S3 just works. You put data into it, you get data out of it, and it scales with your workload. Sometimes data lakes, some applications such as data lakes may actually drive an incredibly bursty workload. And what we call a bursty workload is a workload that starts increasing its TPS very, very rapidly to very, very high level. S3 scales automatically with your prefixes. And when we realized you send a very high number of requests to a certain part of your namespace, we will scale it out. But this process is not instantaneous. Without upfront scaling, the kind of a TPS you're going to get is at least 3,500 on mutations and 5,500 on get operations, such as get and head. And for the most customers, it's more than enough. And for the most customers, this just works. However, there may be some scenarios where you might want to avoid hitting these limits. When you do hit these limits, occasionally your application might experience what is called a slow down error or a 503, and which can be easily retried, and you can typically proceed with your workload. SDKs do it for you as well, so for many customers, it's completely transparent. Nevertheless, if this is something you would like to avoid ever happening because of the unique and bursty workloads, there is actually something you can do. Let's consider an example. Let's say you are running a fleet of autonomous vehicles, so a bunch of instrumented cars sitting in a central depot, and say every day they embark on a journey and they drive around the world, and then they come back in, and for whatever reason, let's say they're not equipped with wireless, they upload all of their data at the very end of the day at about the same time. If you were to design your prefix, it may look something like this. And it's pretty natural, because you have maybe a bucket name called daily uploads, you have a date, you have a car, and drive data. So let's consider what a put pattern may be on this particular prefix pattern. So you will have puts on the keys that may look something like this. And as you can see, as we just discussed, cars upload the data at about the same time. And now if you look at this picture, you will see that there is a big chunk of it that is white. And this is the very wide prefix that these uploads share. Now, because these things share this white prefix, it's very likely that they're going to hit the same back-end S3 prefix. So in practical terms, you may experience something that looks like this. And again, depending on the number of cars, the individual TPS, and variety of a lot of factors, you may observe a pattern that kind of a two-step. So what is happening here? Well, as cars upload the data, the overall TPS good put, that is successful request, scales up and then gets limited because the throughput on a specific prefix has been reached. Again, this can happen in very rare cases when the workloads are particularly bursty. This is a very contrived example. After a period of time, the prefix will scale up and the TPS will naturally increase. And so maybe you don't need to do anything about it. Maybe retry is all you need. But one thing we can do to avoid this, of course, is to spread around the time, the moment of time that we upload the data. But what if that is not an option? Well, we can do something else. Let's revisit our prefix design. As you can see, we started here. What if we did something like this? Now, this deserves an additional conversation. What are these magic numbers that start appearing? Well, we call these things entropy. And entropy is something that is uniformly distributed in a way that is not correlated with the prefix name, something that appears random. It may not be, in fact, random, but it will provide something that provides a uniform enough distribution such that your data starts landing, in this particular case, in different backend S3 prefixes. In this particular case, we use MD5 hash of the car and the date, for example. But pretty much anything will work, anything uniformly distributed. So that will reduce the probability that the keys may end up in the same prefix. And this is just one example. Now, to zoom out, to scale, to design your prefixes for scale, if you can avoid bursty workload on the same prefix, that would be ideal. If not, because you want to organize your data in a natural way sometimes by date, for example, and these prefixes may be hit with very high TPS, which is typical for daily ETL, for example, when you process events for the same day. Injecting entropy at the start can be very useful. Some customers find it very successful rearranging the structure of the prefix, for example, putting maybe car names up front, any combination of things. This recommendation is general and applies to S3. Some products may make assumption about your prefix structure or directory structure. A lot of products, such as Hive and Presto, were designed with HDFS in mind. And HDFS has very different performance characteristics, as we have discussed. So these products may, in some cases, force a very specific prefix design. That said, even those products have features that allow you to make them a little bit more flexible. For example, anything that relies on Hive Metastore may utilize features such as external table or partitions, which allow you to intentionally spread your data across multiple prefixes and still follow this guideline. Another option to consider is manifest-based formats. You probably have heard of formats like Hudi or Iceberg, and those don't rely on any predefined directory structure, but rather use manifest to describe the placement of objects. They also typically provide additional features, such as asset transactions and so on. The main takeaway from this is really that prefixes and workloads should be designed intentionally. And it's the combination of the two that really affects your performance on Amazon S3. There is no such thing as right and wrong design of prefix and workload and separation. It's the conjunction that ultimately makes the most difference. These are prefixes. Now let's talk about objects. In addition to what we have just discussed, size and shape of object matter as well. As far as the size, for those of you coming from HDFS background, you may remember that HDFS prefers very large objects, and that's because of fragmentation predominantly. S3 doesn't have this limitation. You can have tiny objects. It doesn't affect your cost structure. It doesn't affect fragmentation in any way. But preferring large objects can be very beneficial. For one, if you have chunky objects versus tiny ones, you can reduce TPS on your prefixes because to get the same amount of data, you now need to query fewer objects. It also lowers the cost of requests for the same reason and reduces data round trips. We found that the magic number lies somewhere around 10 megabytes. But ultimately, it's specific for your workload. The general thought process is avoiding tiny objects is also a good idea. Format. Formats need to be chosen very carefully for a wide variety of reasons. And this is where we go back to lift and shift not always being the most optimal approach. Because preferring widely adopted formats will result in your data being available for much wider ecosystems. In addition, there are some performance characteristics that can be improved if you use certain formats, like columnar formats like ORC or Parquet, because they result in more compact sizes, better performance, and they also can allow for interesting functionality, for example, like predicate pushdowns, where the filtering of your data is done at a storage level. And speaking of predicate pushdowns, Amazon S3 Select is a feature we released several years ago, which allows you to effectively execute SQL on top of an object and just return the data that matches a certain criteria. It supports several well-known formats, including Parquet, and is automatically supported by Athena and Amazon AMR. So the general outcome of this is that the size and the format ultimately affect your performance in ecosystem integration, and these decisions are very important to keep in mind. Now, when we talk about object size, there is this interesting tension that exists, especially if you have streaming workloads, when you try to ingest data into S3, basically in near real time. As S3 is not a file system, objects in S3 are immutable. You cannot append data to an existing object without overwriting it. And so this tension exists where if you want to maintain objects as fresh as possible, then you may end up with a lot of really tiny ones. And as we discussed, it has its downside. On the other hand, if you make them chunky and bigger, then in this case, the ingestion might slow down. And this is balance. This generally speaking, is maintained based on the nature of your applications. But there are some things you can do to make this easier. One of them is S3 supports multi-part uploads. That could be one mechanism that can be helpful here. And in practical terms, multi-part uploads allow you to upload object part by part. But then when you commit the full upload, basically complete it, then the whole object appears in Amazon S3. You can also, if that is not an option, you can also use EMR, for example, to join these objects later, if that is appropriate. It's a little bit more work, but it may be worth it. And there are other projects in the ecosystem, which I'm going to mention a little later. For example, Amazon Kinesis Firehose can do a lot of interesting things as well, and it will do it automatically for you. Another common consideration when building your data lake is a consistency model. And as you probably remember, most data stores for the longest time in the cloud have been built with eventual consistency in mind. This is something we delivered last year, and we rolled out a strong read after write consistency. And it was a big deal because a lot of our customers, especially those running data lake workloads, actually need to rely for correctness on the fact that the moment this object is written, it can be immediately accessible to all readers. That was not always necessarily the case before last year, and now it is. Another factor that I would like to discuss is cost, because this is another thing that we were having trouble managing in our previous solutions. Amazon S3 provides what we call a storage class. It's a fairly deep subject, but you can think about them as sort of a dial, which allows you to optimize your cost based on your use case. In evaluation which storage class to pick in S3, there are several factors in two main groups. One of them is access pattern. How frequently is your data accessed? What sort of latency and availability is expected? The other one is duration of storage. How long do we store data? And we have a huge selection of storage classes. In fact, we added one this year. I'll mention it in a second. Let's look at all of them. As you can see, it's quite an impressive lineup, and if I go through all of them one by one, we will probably be here until tomorrow. But I would like to mention a few and the decision-making process that may be helpful in understanding which storage class works for you. The natural place to start is S3 standard. In some sense, it's the default. It's what you get if you do nothing. It is designed for 4 nines of availability and millisecond latency and protection against single AZ loss. This class works well for pretty much anything, but it's most optimal for hot data, the data that gets written and read very frequently and maybe doesn't last all that long. On the flip side, in some sense, there is what is called infrequent access. As the name implies, is if your data is less frequently accessed and not deleted within a month, you can save actually close to 40% of storage cost. There will be some retrieval fees, but other than that, but they're relatively minimal. So if your retrievals are not very frequent, this is a great cost-saving feature. There is intelligent tiering storage class, which is actually fascinating, and it's the only cloud storage class that delivered automatic storage cost savings by transitioning data in a clever way, and I will cover it in a little bit. We also provide, you can also archive objects using Amazon Glacier, and that reduces your cost even further. And in addition, we have a variety of other offerings, including a single AZ offering, infrequent access, and otherwise. One thing I would like to mention is one of the storage classes that we shipped this year is S3 Glacier Instant Retrieval. And this is a fascinating class, which is a archive priced class, but with millisecond latency. For those of you who have used Glacier before, you're probably familiar that when you place data in Glacier, it may take minutes or hours sometimes to get it. In this particular case, that is not the case. It's a little bit more expensive, but for some workloads, it can be a very good choice. So how do we apply all of this practically? And most importantly, how do we transition between the storage classes? Because clearly, it really depends on how your data is getting used. And as the data travels, it typically changes temperature. Something that may starts very hot may actually cool down over time. Well, there's 2 primary mechanisms. One of them is the Amazon S3 lifecycle. And it works really well for what we can describe as predictable access patterns. It may transition from class to class based on the rules you define, based on prefixes, tags, and bucket configurations, as we have discussed before. And it can even transition it to a deep archive. Now, a lot of data doesn't really have a very predictable access pattern, or maybe it's unknown. You can actually have Amazon S3 analyze your access patterns and move your objects automatically. Let's take a closer look. As it turns out, the vast majority of data has unknown and predictable patterns. And for these classes, we have a tier access that automatically optimizes storage class based on the access of this data. So if your data is hot, it is going to stay in the standard. And as the data starts cooling down, it gets transitioned into infrequent and even instant Glacier Instant Access tier, and even into a Glacier Deep Archive in the end. This actually takes a lot of thought out of this, and the intelligent tiering we recommend considering for pretty much all of your data lakes, unless compelling reasons exist otherwise. So how would it look like for a very simple example? Let's consider of applying this to a simple data lake. It's a very simple architecture. You have a raw data pouring in, you have a ETL working on it, you have a production data lake that gets queried, and at some point you need to archive your data. For raw data in ETL, because it stays largely hot, standard data layer may be appropriate, standard storage class may be appropriate. Intelligent tiering may work as well, especially if your buckets contains other types of data. For production data lake, you typically observe patterns when you have older data and newer data, and intelligent tiering is actually the best match. And finally, for historical data, Glacier, Glacier Flexible Retrieval, and Deep Archive can be great options. So if you take out one thing out of our conversations about the storage classes, it is that S3 intelligent tiering is a layer to consider and it takes a lot of work out of deciding how to transition your data across storage classes. We know that customers, since we shipped this layer several years ago, saved a lot of cost using this tier. You can't really manage your cost effectively without understanding where your money goes. And so to address that, we delivered a product last year called Amazon S3 Storage Lens. It was launched at the last reInvent. I'm not going to go through very deep details. We had several talks to reInvent about this already. But it provides a number of usage and activity metrics, drill downs in a variety of ways. You also have, it also makes recommendation for cost efficiency. And this year we delivered Amazon Cloud Watch publishing for this feature, which allows you to support things like alarming based on your cost usage. Let's briefly talk about ecosystem. As I mentioned before, if I was to try to cover the entire world of all of the things that you can do on top of S3 with AWS services alone, would be here a very long time. So consider this again, a jumping off point, a maybe semi-representative samplings of things you can consider. This is a high-level diagram, and you can see that you can use a lot of Amazon services to ingest, prepare, and analyze your data. And in fact, if they were placed onto this same slide, it would probably be too tiny for you to read. Let's start with ingest. First of all, Amazon S3 can be used for ingest. Sometimes it's all you need. After all, it's a simple storage service. It can be looked at as an ingestion layer. All you need is put, maybe multiple, maybe MPUs. AWS Lambda is a serverless event-driven compute service that lets you run Coast asynchronously. And it can be activated on each put, which can be configured to be activated on each put, which allows for data transformation. That actually can be very handy for ingest. Amazon Kinesis Firehose specifically can be used to stream data in Amazon S3. And remember we discussed the size versus freshness trade-off. Amazon Kinesis has a very sophisticated machinery to do it right. Based either on it allows you to control the buffer size as well as the time window in which data gets flushed. The data sync employs an AWS design transfer protocol to accelerate data movement. It allows you to pull data out of your existing data sources and push it into S3, either as a snapshot or as a replication-like functionality. It also supports a very wide set of formats. Note that this is a very small subset of what we provide in S3. For example, Snowball family allows you to literally ship your data on a truck to a AWS data center. And this is very useful for large data movements or if security is particularly important to you. Another group of services is ETL, a catalog. Remember when we, in the big data swamp site, we're discussing how difficult it is to process data and how difficult it is to find it. Again, you can use Amazon AMR for processing your data and running ETL, similar how we use any other Hadoop distro. Amazon AMR supports Spark, Hive, and Presto, and it can be used for batch and stream processing, like you always did before. Again, Lambda can be used for ETL as well, because it can be triggered on individual puts, and some customers build pretty sophisticated data pipelines with, where data slowly jumps from one bucket to another. Amazon Glue, AWS Glue, is a serverless data integration service that makes it easy to discover, prepare, and combine data from analytics, machine learning, and application development. It basically provides you with a managed ETL functionality, and some of it can be visually designed, and people get very far with just the Glue Studio. And another thing to mention is Glue also provides a catalog and a set of crawlers that automatically discover your data. And that sometimes can really help to overcome the swamp situation when you don't quite know where your data is or how it's being accessed. Analyze. Well, presumably you have data in your data lake to do something with it. And this is one of the most common things we do with our data. Amazon AMR is something that is a good fit for Hadoop-like workloads. One of the things I would like to mention is that it's optimized specifically for Amazon S3. And that exists on several levels. First of all, as you may remember, Hadoop provides its own file system abstractions, and Amazon AMR comes with one. AMRFS, which does a lot of smart things behind the scene. In addition to it, it also automatically puts in play commit protocols that utilize multi-part uploads over copying data from multiple locations. Generally speaking, people get a lot of good performance out of the box by using Amazon AMR. It also natively supports in the later version S3 Select, which can achieve improvement of both performance and cost by an order of magnitude. You can also continue running whatever distro of Hadoop you prefer on EC2 and use S3 from there. If you do so, please make sure to consider S3 optimized committers. There is a lot of open source community engagement that is specifically that is specifically targeting S3 as a data store and ensure that the commit protocols are as fast as possible. Again, Amazon AMR will do it for you by default. Amazon Athena is a serverless offering, and it's originally based on Presto. And for some scenarios, it's perfect because you don't need to scale your cluster, you don't need to allocate your instances, it just works. I mentioned Amazon Redshift here because this is a data warehousing solution. This is where you can load a lot of your data specifically for reports and to expose to reporting software. And because it provides on the outside effectively the same shape as Postgres, a lot of software can use it directly. And there is many, many, many more other services. Here I mentioned Amazon FX for Lustre and Amazon S3 File Gateway, which allow you to use S3 as if it was a file system. Amazon SageMaker is, of course, Amazon machine learning solution, which can utilize S3 directly. And I mentioned Amazon Open Search Service, which is in some ways a successor of Elasticsearch, because it actually can be seamlessly integrated with S3 in several ways. One of the interesting ways people integrate with this is, again, using AWS Lambda. Is your object get placed into Amazon S3, you can activate a Lambda, process the object, and inject whatever information you want into the Open Search Service. And now let's jump to the last subject, which is security, compliance, and audit. Again, this is a very deep subject. In fact, I believe at the Venetian there is a separate talk entirely on this, and we were having trouble squeezing it into 1 hour. I'm going to point out some of the things that are particularly important. First of all, Amazon S3 provides granular and fine-grained control. And this is very important to data lake because it allows you to give your customer access to what they need and nothing else. And the nothing else sometimes is very important. And to do that, you can utilize IAM and bucket policy. Now, you may remember that when Amazon S3 came out originally, it relied on ACLs for security. In fact, we still do. And I'm going to mention why I'm not talking about it right now in a second. Access points is a very interesting deliverable because it simplifies managing and securing data access at scale. And what you can think about access points as views on your buckets, sort of a virtual buckets in some sense. It allows you to do things like completely lock down your bucket and expose several access points that have access only to certain sub-prefixes. That allows you to have a singular storage of data, but have, for example, give different access points to your finance, to your engineering, to your C-level executive, and so on. Two of the very important Amazon S3 features in the security space is block public access and object ownership. And these things that actually disable stuff. Block public access allows you to completely lock down your bucket to make sure they never, ever are publicly available in the internet. By default, for historic reasons, we allow this because a lot of people run websites directly off of S3. But in enterprise environments, it's typically not a very helpful thing to do. And this year, we delivered what we call S3 object ownership, and that allows you to effectively disable ACLs. And so the only security policy, the only access policy that's going to apply is IAM and bucket policy. There is also a lot of other features in Amazon S3. One of the other things I would mention is object lock. It supports basically a worm model, which makes, for all intents and purposes, certain object immutable. And you can use it to meet a variety of regulatory requirements that require this sort of semantics. Conversation about security would be incomplete if we don't talk about encryption support. As Amazon S3 offers encryption in transit and at rest, you can use encryption SDK to encrypt data before it leaves your company infrastructure. S3 will never see any plain text. Amazon S3 also supports encryption on the wire versus HTTPS. It's worth noting that while you can, in theory, allow access to your buckets via HTTP as well, we don't recommend it. And in fact, you can configure your bucket such that you can disable it, and all of the plain text traffic will be rejected. And finally, on the server side, we provide several types of server-type encryption, server-side encryption, with a lot of flexibility that typically matches one of the requirements that you need. This slide is really not meant to be read in detail, and it's a subset of all of the certifications in the secure infrastructure space that AWS consistently working on and increasing, and all of them apply to S3. And there is much, much more. This is just the tip of the iceberg. AWS provides a large and growing set of services to enable you to build, catalog, secure, set, and manage your data in S3. In addition, it provides a large set of tools to read, analyze, and process data. As I was trying to say before, we continuously innovate on your behalf, so you don't have to. And as a reminder, if there is one thing you take out of this presentation, it would be this slide. Decisions you make when you design your data lake matter. Hopefully this presentation helped you understand how they impact it. Thank you very much. It's been a pleasure being here.